Okay, this is the symbol for NPN transistor. You can see you get two different transistors. One we call a NPN. This is NPN. And this will be P and P. Okay. Now see what's going on. So basically, we're talking about NPN first. They get that one will be a base, collector, and emitter. Okay. Same thing for PNP. The difference will be the arrow NPN going up. The arrow for PNP coming in. That is the difference. Okay. And now for NPN at the base, you get the current coming in, IB. Collector, you get the current coming in, IC. And the emitter, current leaving. Okay. And if you see the formula here, basically IE equal IB plus IC. Okay. And also you can get alpha can be defined as the IC divided to IE. And the beta equal IC divided to IB. Okay. What I expect you to know, when you see the symbol, you know that NPN transistor or PNP transistor. That's the first recognize. The second thing is the current flowing. NPN IB going in, IC going in, IE leaving. PNP, then the current IB leaving, IC leaving, IE coming in. This is the formula applied for both. Okay, doesn't NPN or PNP. Okay, any question? And make sure you have to download the handout number 3. That's what we're talking about. Okay, this is a little more physical. Okay. NPN here. This is the N. Okay. This is the N and the P in the middle. N side contain electron. Okay. P side get the hole. That means when electron can be moving, that means the current will be flowing. And this is the PNP opposite to the NPN. You can see that P side, N side in the middle. Okay. And NPN will be N, P and N. This is physical, okay? When another section of P or N type material is added to PN diode junction, a three-section device containing two junctions is formed. You understand the diode, okay? Diode, that means you get a PN, that's a diode, okay? So basically you get two diodes, PN one diode, PN another diode. Same thing, PN one diode, PN another diode. Basically two diodes will make it up the transistor, okay? And this is the one NPN, and this is a PNP, okay? So in general, you understand, you get two diodes, okay? The thing we already learned, diode, PN, okay? That's a diode. Now, you can see NPN, the base here, you get a one diode go to the collector, another diode go to the ammeter, and the voltage of the diode will be 0.7 volt, okay, NPN, and that's a PNP. You still get the same two diodes, but the difference will be ammeter and the diode coming in, collector coming in, okay, and you have to know the current flow, okay. For the base, IB go in, collector, IC go in, and ammeter, current leaving, okay? And this PNP opposite. And that also they given you the transistor. When you're working on the left volt, you will be using that, okay? Number one, ammeter, number two, the base, and number three, collector, okay? Make sure if you get a question and you can stop me, okay? First lecture today, we're talking about DC bias. What that means? Without a power supply, you cannot turn on the diode, okay? That means the transistor cannot working without the power supply, DC, okay? And after you know how the transistor will be working for the bias, DC, then we go to the next one. Lecture will be talking about transistor will make the amplifier. Okay, now you see NPN circuitry here. You get a VCC connect to RC, okay, and VBB connect to RB, okay, and you understand I'm talking about NPN, okay. Basically, this is a positive here. This is a negative, and that value will be 0.7 volt. How come? How come you get a 0.7 volt? The thing is this, the diode, okay? If they on, positive here, negative here, 0.7 volt. Okay. So what we have to do, and we try to calculate what the VB voltage, what the VC voltage, whatever related. And if you're looking into here, this is the base. This is the collector. And that ammeter. Okay. If I want to measure the VB, so you get a DMM. Positive connect to where? VB. Okay. Then DMM. High. DMM low. Connect to. Okay. DMM high connect to where?
The base.
If you still want keep moving, you have to tell me.
Letter B, the base.
Connect to. Right? And DMM low connect to where?
Ground.
Wow, perfect. Okay, when you measure at a single point, the other point of the meter must be connected to the common, to the route. Okay, now if I connect to measure VCE, DMM high, okay? If I want to measure the VCE, that means from C to E. DMM high connect to
connect C.
DMM low.
Back to ground.
Basically, you have to say, right? This case, they connect to route. However, if you want to measure C to E, then you have to connect to E. Okay?
Hey, Mr. Pham,
Yes, sir.
the reason you want to connect C to E is because in the emitter part, if you had a resistor there, then you couldn't connect to ground.
Perfect.
That's why you need to connect from C to E.
Right.
Because if a resistor's there and you connect to ground, you're really not measuring the resistor, you're measuring VCE, not C to ground.
When I said I want measure VCE, high side you connect C, low side connect to E. In this case, they connect to ground. That doesn't matter. Okay. If I want to measure VRC, okay, DMM high, DMM low. If I want to measure the voltage across RC,
From the VCC to C.
that will be VCC, correct? How about low side?
To C.
I want VRC. That means from here to here. So you say the high side connect to VCC. Okay. What about low side DMM? Connect to
Letter C.
collector. That's a minimum requirement. Okay? You must know. Okay, again, if I want to measure the RB, then the high side connect here, low side connect to B, across RB. Okay, that's a minimum thing when we asking you, you have to know. If the basic, very, very basic, you don't know, how can you can learn it now? See this circuit. Okay, you know this is the base. This is the collector admitter. Okay, NPN transistor. IB going in. IC coming in. IE leaving. Okay. So now you see they're talking about VBE. What that mean? That means the voltage from the base to the admitter. That means from here. And the diode on, they're telling you you get VBE equal 0.7 volt. Okay, and now you can see they given everything right here. This is the formula, okay, equation. They draw the loop in here. Okay, when you go into the negative, they get minus. Okay, this is the minus here. This is the positive here. You want to draw the loop current You go this way. Okay, when they hit into VBB, they hit into negative, so that's why you get minus VBB. That's the first thing. After that, they go to RB. That's why the current will be IB times RB. That means you get the voltage. You plot IB times RB. And you hit 0.7 volt, positive, negative. So that's why plus 0.7 volt equals 0. Okay. From this coming up with IB. Okay. IB equal VBB minus 0.7 volt divide RB. Okay. And after you get IB, you can calculate the IE. They want you to using this formula. IE equal 1 plus beta. Beta means the current gain of the transistor be given. Okay, time RB. And also you can calculate the IC equal beta time IB. Okay. In case you want to calculate the IB, you using IE divide 1 plus beta. The formula they given to you. Okay. You get IB. You get IC. You get IE. Okay. And you know IE equal IC plus IB. And also you know IC equal beta time IB. That's a very, very basic formula for the transistor. And beta means current gain.
Hey, Mr. Pham, beta is a ratio, is that correct?
Yeah.
And do you want the ratio to be high or low?
What do you mean ratio?
The
Beta?
beta is a ratio between IB and IC, is that correct?
Right.
So
However,
my question is, do you want beta to be high or do you want beta to be low?
yeah, beta will be equal IC divide IB.
Yeah, I know that, Mr. Pham, but I'm asking you, do you want beta to be high or low?
No, depending on what they given to you. You cannot decide what beta equal.
Okay.
Beta, that the current gain of the transistor be given to you, depending on what NPN transistor you're working on. Okay? That's given. So all of that formula will be helping you. First thing you can calculate, okay, IB, calculate the IC, IE, okay? And also you can calculate the VRC, Okay. That means the voltage across RC here, VRC, or the voltage across RB here. Okay. They already given to you here. You need to get to it. Okay, now you can do it. First thing, VBE. That means here, B to E. And basically, they are get a diode. Okay. And the diode will be 0.7 volt. Like I already telling you. Positive here, negative here, 0.7. That means from B to E. That's a one diode. And that's 0.7. Okay, so now the next, you can calculate the IB. Okay, I can give you a little help here. If you draw the loop current, first thing you hit 5 volt minus 5. And you adding the voltage here, VRB. VRB, that means IB times RB. And you hit into plus or minus 0.7. Plus 0.7 equals 0. From this formula, okay, you can get IB times RB equal you moving minus 5 to the other side, 0.7, same thing. Minus move to the other one, equal 5. 0.7 move to the other side, have to be minus 0. So you get 4.3. And now IB equal 4.3 divide RB. Okay, so now what you need to do, go ahead, calculate the IB to see you get what we wanted.
IB
I
or
already
R?
telling you right here. Okay, go ahead and calculate to see you get 0.43 milliamp.
Can.
Right or wrong?
Can.
IB equal 0.43 milliamp, correct or no?
Yes.
Okay, that's correct. So 0.45, 43. Okay, if you want to calculate the IC, and you know IC equal beta IB. And they already given to you here, beta equal 100. Okay, so basically you take 0.43 times 100, that given to you
Mhm.
43, right?
Yep.
And now you calculate the IE. Okay, I'm telling you, IE equal 1 plus beta times IB. We don't want to using the formula IE equal IC plus IB. The thing is, the current is too small. You calculate by that formula, not more accurate. So that's why they want, if you want to calculate the IE, you know IB. You better using the formula 1 plus beta times IB. In here, okay, I did calculation. I get 43.01.
Okay. That's 101 times 0.43, right?
Okay, 1 plus beta mean 101. Time IB time 0.43. So my calculation 43.01 milliamp.
No, no, it should be 43.43.
Can you say again what?
It's supposed to be 43.43.
Okay, now I
I
got,
get 43.43 also.
okay, that's just a minute.
Bogart answered all.
Go to page one.
Fred Bogart answered all.
101.
Page one has IE,
Ah.
IC plus IB.
Okay, 0.47, 43.
Yes, you can
Okay,
tell
43.43. Correct, you correct.
Fred Bogart.
Thank you.
There, Red Bogart.
Okay, now, next, they want to know VB. VB means the voltage at the base to the ground. That means from here to the ground here. You know that will be 0.74. Okay, if you not agree with me, let me know.
Uh-huh.
And then they want to VE right here. That means from here to round. Basically, VE 0 volt. Correct?
Okay.
Okay. And next one, VC. VC right here. Okay, the formula to calculate the VC I given to you. Okay, VC equal the difference voltage between 10 volt VCC and the voltage drop across RC. VC equal VCC minus IC times RC. Okay, calculate to see you get 5.7 volt. Okay, who get the 5.7? Correct or no?
I got 5.7, Mr. Pam.
Okay, 5.7.
8.
Last one, VCE. You understand the
The same answer. 5.7.
VC, that's a 5.7, right?
Right.
Mm,
Now, if you want VCE, basically definition, VC minus VE. Okay? VC 5.7 minus 0. That you get 5.7.
So,
Mhm.
That's the first example. Very, very basic. Okay? You have to try to understand. Not too many formula. Okay? Any question regarding into this example?
No.
Okay, if it's not, now, if you're looking into here, okay, they get a reason for operation of the transistor. First thing, cut off. Okay, cut off that means transistor will be off. Okay, they using in switching application. That means just on or off. Okay, next region will be active. Used for linear amplification. That means they're using as an amplifier. Amplify the signal. And the next one, saturation. Same thing, used like in the switching application. Okay, that means either they on or they off. Breakdown can destroy the transistor.
Hey,
So
Mr. Pham, so we
basically,
want to use the transistor in the active region, right?
if you want to be amplifier, then they have to be inactive. However, if you like to turn it on or turn it off, then they have to be in saturation or cut off. Like you turn your switch light, turn on or turn off. Okay. Cut off diode from B to emitter E off. You get the diode here. If they off, no current flow. Okay. If no current IB, no current here. Okay. Active diode from the base to the emitter is on, and the diode from base to collector is off. Okay. Basically, in here, you get a one diode here and one diode from collector to the base. Two diode. Remember, transistor get two diode. Okay. For NPN, you get a one diode here, C to B, and another diode from B to E. So, for active, diode from the base to the emitter is on. Okay. Base to emitter is on. And the diode from base to collector is off. Okay. If saturation, both diodes are on. And VCE equal 0. That's the minimum thing we have to know. So basically, they can be cut off, transistor can be active, transistor can be saturation. Okay. So when the transistor be cut off, okay, that they telling you the diode from the base to emitter is off. Then you know transistor cut off. Okay. For the active, then the first thing the diode from the base to emitter is on. However, another diode from the base to collector will be off. And finally, for saturation, both diodes will be on, and the VCE equal 0. Okay. That you need to go over. Okay. When they asking you, you can easy to answer.
Sorry, I was hoping for a reminder. For saturation, it says VCE is 0. Is that because it's in the ideal state?
Yeah.
Okay.
The thing is, if you said if the transistor is saturated, then you have to say both diodes will be on. And that will be given to you. VCE will be very close to 0. Okay?
Okay. Thank you.
Yeah. Now, example number 2. Now you can see more easier. This is a VE. Okay, you don't have to draw the loop current like the previous one. That VCC, RC, VE. Now, for transistor in the circuit shown, what is VCE when V in equal 0? Okay, now, if they given 0 volt here, the question is, what is VCE?
I think according to your notes, it would be 0 because you have no current flow.
Okay, first thing, you can understand IB 0, correct?
Correct,
IC 0,
correct,
IE 0.
correct.
Okay, so now they asking VCE. Okay, VCE equal VC minus VE. Is it correct?
Correct.
Okay. And equal VC minus 0 equal VC. If something is not right or it's confusing, let me know. VE connect to the ground, right? So that's why VCE equal VC. So what do you think VCE equal?
VC.
It's 0. They both, there's no current flow, right, Mr. Pam?
My question is, VCE I already proved equal VC.
Okay, that's 10.
So equal what?
10?
You
I
good.
say 0.
Okay, now I telling you. Okay, IC equal 0. So the voltage drop here. VRC
Equals
equal
0.
what?
0.
0. You get a 10 volt here. They drop 0. So VC have to be equal VCC.
Oh, I see what you're saying.
Okay. So finally, VCE. Let's see. I better draw this way. VCE equal VC minus, okay, 0 VC. The thing is, I want to drop across RC, okay, equal 0. Okay, VC basically equal VCC minus IC time RC. Okay, and this IC equal 0. So that's why IC times RC 0. And they will be equal okay.
10 volt.
So let's see what they try to explain to you here. When V in equal 0, transistor is off. IB equal IC equal IE equal 0. Okay? Therefore, VC equal VCC equal 10 volt. The voltage drop across RC equal 0. Okay? VCC VCE equal VC minus VE. Okay? Equal VCC. Number 2. What minimum value of IB is required to saturate this transistor if beta is 200? Now, see what they're telling you here. Since the transistor is saturated, that already know VCE equals 0. Like we just talked to you. If they saturated, VCE equals 0. Okay? Then IC saturate equal VCC divide RC. The thing is, VCE, that means the voltage from here to here is 0. Okay? So that's why the current IC you can calculate, okay, equal VCC divide RC, given you 10 milliamp. Therefore, IB equal IC saturate divide beta. You get 10 milliamp divide beta equal 200. So you can get 50 microamp. Okay. Calculate the maximum value of RB when V in equal 5. That means the last one they given to you 5 volt. Okay. So
Hey, Mr. Pham, I hate to bug you, but what was beta in that previous one? I mean, what was IB?
IB or ID?
Okay, it says what minimum value of IB. So you flip-flop the formula around, correct?
No, okay. We're talking about transistor saturate, IC saturate equal VCC divide RC. Okay. That means you can calculate the IC saturate. equal 10 milliamp. Okay. Therefore, they're telling you IB equal IC divide beta. We already know that, right?
Mm-hmm.
IB equal IC. Okay. So that's why you can calculate the IB equal 50 microamp. However, the next one, when the transistor apply 5 volt here, okay, calculate the maximum value of RB when V in equal 5. That means they don't know what the value here, okay, but they given you 5 volt here, okay. Then basically, if you get that 5 volt, so basically the diode here on, okay? So you can see very simple equation, okay? Minus 5 plus IB times RB minus 5 plus IB times RB plus 0.7 equal 0. Then now, okay, you can see IB times RB, okay? IB, RB equal, you move minus 5 to the right, you get 5. Move 0.7 minus 0.7. So basically you get IB times RB, okay, equal 4.3. IB okay. So if you want to get RB, you take 4.3 divide IB. Okay, they can already telling you in here. When the transistor is on, voltage across RB, VRB equal V in minus 0.7 equal 4.3, and RB maximum VRB divide IB minimum, okay, 4.3 divide 50 microamp. Let's see, IB equal 50 microamp right here. Okay, so the answer will be 86 kilo ohm. Sometimes you guys need to go over, okay, this example to make sure you know how to do your calculation. a little more confusing. Okay. Okay. This is a graph of IC versus VCE. You understand this for IC in milliampere. This stands for VCE in volt. Okay. And X line here stands for the current IB. That IB. Okay. Now, at this point here, current IB equals 20 microamp. And on this line, 40 microamp and so on. Okay. And the transistor, we already telling you, they can be saturation, they can be cut off, and they can be active. Okay, if you're looking into here, you know that's a saturation region. Saturation. You see that? Saturation. Anything in here telling you transistor is saturated. Okay? And another part here. This region for the cutoff. Okay? So, anything in here will be active. Okay. That you try to understand, but not for you. That's for engineer. If I want to using the transistor to design the amplifier, okay, then I don't want that transistor to be saturated. I don't want that transistor to be cut off. So basically, I want they will be in this area. For example, now I get the point in here. I call a Q point. Can you telling me at the Q point what current IB? What current IB equal at the point Q point?
60 microamps.
How many?
Let's say 8 milliamps.
I asking about IB.
20.
There's nothing there.
What?
Yes,
Yes.
2.5.
60 microamps.
Perfect. Right here. You can see right here, Q here. You go in here, 60 microamp. You see that? Now, what is the IB? Then you can go to the lab, that will be IB. Okay, you see that? What the VCE?
Oh, you mean like 10 volts?
Volts.
Cut off 20.
You want this stand for VCE. That stand for VCE. Q point here. You want VCE, you're going down
10 volts.
10 volt. You see that? At the point Q, you're able to know what the IB equal,
By the
what the IC equal, what the VCE equal. That's what they call Q point.
Hey, Mr. Pham, so we can also tell what beta is too, right?
You say, can you say again?
We can tell what beta is because we can look at the IB and the IC and divide IC by IB and we'll know beta. Is that correct?
Yeah. That means if I give you a Q point, you're able to identify from this
Okay.
graph what IB equal, what IC equal,
Okay.
what VCE equal. Now, if they already know what IB equal, what IC equal, VCE equal, okay, they can, from that point, they can go ahead and calculate to see what RB equal, what RC equal, what RE equal. You know, you can get the MSIM7. Also, another simulation, P-SPI. That means if you already know the value, you can get the resistor R, B, R, C, R, E. Okay? To make the transistor working at the point Q. Why they don't want to pick Q here? Okay? Why they don't want to pick the Q right here or here? You know why? The thing is when you design the amplifier, you want that amplify your voice. Okay? If you select the Q point close to the cutoff saturation, when the temperature go up, they can move that Q to saturation. That means no more amplifier. That's not good. And they don't want any point very close into cutoff. Okay? When the temperature changes, they can go to the cutoff, no more amplifier. So that's why they have to pick in the middle. They can move a little up, they can move a little down, but they still active. Okay? Finally, on this one here, okay, basically transistor, okay, be controlled by the current. Transistor NPN or PNP. A current controller. Remember that That means when you change the IB, okay, then everything will be changing. Okay, so that's why they're talking about NP. Transistor will be controlled by the current or current controller. Later on, you will get another transistor that will be JFET, okay, pure effect transistor. They're not controlled by the current, okay? That normally, when you interview for the job, they just asking you in general, okay? Transistor will be controlled by what? Current or voltage, okay? NP, controlled by the current. That means you can change the current IB and everything will be changing. Okay? Basically, they say this set of curve is also called a family of curve. Okay? So when you're looking into the graph, you're able to recognize what IB, what IC, what VCE. Now, the next, they want to draw the load lines. How to draw DC load line? The purpose is what? When they draw the line, they're able to pick, okay, any point in here. You can pick a point in here, you can pick the point in here or here. So they need the line. Okay, this curve go with the transistor. Okay, and the pick the point, any point, kill here or here or here. Depend on the load line. So you learn when you want to draw the line, you need 2 points. First thing, you need to identify point A. Then you will get point B. You draw the line from A to B. That's what they call load lines. Now, they're telling you, point A at saturation, okay? At saturation, I saturate equal VCC divide RC. Okay, you take up 10 volt, divide 1 kilo ohm. That's what you get the I saturate. Okay, this is the I saturate here. Okay, 10 volt divide 1K, you get 10 milliamp. That means this is the 10 milliamp. That's a 1 point. Now you need a point B. Point B at the cutoff. Okay. That means when they cut off, then VCE equal VCC. Okay. So basically, you equal 10 volt. So now you draw the line. Okay. They're telling you the load line. Again, to draw the line, you need 2 points. So we have to identify what point A and what is point B. In here, they already telling you point A at saturation. Okay. And also I saturate equal VCC divided RC. We already calculate before. And they can be 10 milliamp. So you get 10 milliamp. Okay. Cut the curve right here. 1 point. The second point will be B. Okay, point B at the cutoff. This is the cutoff. Okay. So VCE equal VCC. You connect from A to B. You get the line they call a load line. How to draw it. Okay. The next one. Let's see. Bipolar transistor mode operation. First thing, you can be, again, transistor, they can be active for amplifier. They can be saturated or cut off, that's just for the switch. Okay. Now they given to you example. Cut off, like collector to add meter, you get open. You see that? Get open right here. They can close, they can open. That's like the switch. Okay. Saturation. Close the switch. Okay. And this is VCE equal 0. So either cut off or saturation. Cut off, they let the switch open. Okay. Saturation, they close here. No amplifier. Okay. Okay, this is example number 3. Okay. Your guys supposed to do it. Like they want to calculate the IB. Okay. That means I already calculated. Okay. You can draw the loop here. You can get IB. After you get IB, you can get IC. You can get IE. Okay. VE, you know 0. VB, that means voltage from here to the ground. I know they will be 0.7. VC, that means equal VCC minus ICRC. Okay. And VCE equal VC minus VE. That means everything we already did it. Your job will be try to go to calculate it. Okay. Make sure next time we can get. Okay. Basically in here, they already calculate for you. Okay. They already calculate for you. Calculate the IB. Okay. You can go through that. IB 0.043. And you can calculate the IC. Okay. IC equal beta IB 4.3. And then IE, VE, VB, VC, VCE. Okay, we already done. Example number 4. Let's see. determine Q point for the circuit shown. Given beta 200, that means you need to calculate IB, IC, IE, VCE. Okay? So, first thing, you want to calculate IB. I given you a little help here. You know that will be positive, negative. Okay? So now you see you draw the current loop. You can get minus 10 plus IB, RB plus 0.7 equal 0. So now you can get IB times RB equal 10 minus 0.9.3. And that will be get IB equal 9.3 divide 47K. Okay? So after you get the IB, you can calculate IC equal beta times IB. You can calculate the IE. Okay? And you can calculate the VCE, mean VC minus VE. Everything we already calculated. Okay? And what they want you to get the point A here and point B here to draw the line. That means they want point A here, point B here. In order you can draw the line and draw the DC load line. To draw the load line, we need to know the point A at IC saturate and point B VCE cut off. You know that will be VCC. I believe VCE right here will be 20 volt. B, and that will be A. Point A at IC saturate. That's what they want you to draw the line. Okay. Now, solution. That means in here, they already get a solution for you for the example number 4. Okay. Hopefully, you can go through it. And any confusing, anything else, next meeting, you can bring it up. Okay. We can help you. Okay, this is the same thing. Okay. NPN. We already, this is all of the formula. We already gave it to you. They want shown for IE. Okay, and VCE. Okay. Everything they already calculate here. You can go through that. Now, another feedback buyer. emitter feedback. That means they connect this way. Okay. They will be called emitter feedback. They say better than bias. However, the Q point will be moving, not using popular. Okay, so we never try to solving this emitter feedback. If you want, you run a MSIM 7. They can give you everything. Bias. Okay, let's see. That one they connect RB here, RB here. Okay, bias. Look like the same, right? I see. However, you can see the difference. This get the resistor here. This connect direct to the ground. That is the difference. Okay. The least predictable Q point move with replacement. Q point move with temperature. That is not practical. So basically they never using that to design. Collector feedback bias. Another bias. Okay. If they connect this way, better than emitter feedback bias. Q point still move, limited application. You understand it in general. You get the Q point here. You want that to be in the middle. You don't want it keep moving up or down. Okay? That amplifier will be not stable. So that's why they get too many different types of the bias. Okay? But they're not using. But I listing here for you so you can see. Okay? That will be collector feedback. Two power supply. Okay? You get the one power supply here, positive, another power supply, negative. That means you need two power supply to make the transistor working. Okay? Answer will be very stable. However, you need two power supply. That's what they don't want. The thing is cost power supply will be more. Okay? One power supply good enough. But two power supply cost your guy more money. So basically you can see most of the time they're not using two power supply. Okay? So this is just a little example here for you. One using positive 10 volt, one using negative 2 volt. Okay, if you want to find the voltage, okay, you can go through that. Okay, because they're telling you what we see equal. Okay, that means the collector here and VCE. That means from C to E. That will be E. C here. That will be E. They want VCE. Okay. Last one. Voltage divider. Bias. If the circuit tree connect this way, they using R1, R2. They call a voltage divider bias. You can see this is using all the time. Why? They can using to register, okay, substitute for any power supply in the base, okay. Power supply cost more, like you're using VBB, okay, then they're using R1, R2. You get a VCC. They can using the voltage divider to calculate the VBB. Substitute for another power supply here. Power supply can cost, about $30, $40 of to get the power supply. However, register R1, R2, okay, about 10 cents for 8, okay, much cheaper. So that's why this is the way to bias the transistor to make the transistor working. They're using voltage divider. In here, they given you everything. VBB. You want this voltage here. You take a VCC times R2 divide R1 plus R2. That's what we call a voltage divider law. Okay. And after you get the VBB, okay, then you understand this is a positive. This is a negative 0.7 volt. So you already get a VBB. You want to calculate the VE. Here, they're telling you VE equals VBB minus 0.7. And after you get the VE, you want to calculate the IE. IE equals VE divide RE. This is a wrong one. You correct that. RE. Okay, not IE. And if you want to calculate the IB, IE divide beta plus 1. Okay. R1, R2 form a voltage divider. Okay. So if you want to get the IC equal beta times IB, VRC, that means the voltage here, VRC, equal IC times RC. And now you want VC. VCC equal VC minus voltage drop IC times RC. Okay, so basically this is a summary on of the equation you will be using. And this will be using on the time. Okay, try to get along with the voltage divider bias. This is try to explain everything for you. Okay, you need to go through that. Okay, like I already talked to you. Okay, and they can telling you how to get VB. Okay, and now I in. That means register looking into the base. And this one is not applied for your guy, okay? That's for engineer. They want to go more detail, okay? If you want the RB, that means the register from the base to the round. You easy to measure it, okay? And this part in here, we don't care much thing, okay? If R in base, they will be beta times RE. And on this one, what they want you to calculate, VBB, VE, IE, IB, IC, VRC, VC, VCE, everything. You have to do it, okay? Next time we get in the meeting, I will be asking you, make sure you calculate it, okay? Oh, man, we already given to you, okay? However, this transistor here, what the transistor here?
You mean like the type of transistor?
No, transistor you get only two,
Basic,
one NPN, another PNP.
that basic, right?
So this one will be,
Basic, yeah.
right?
NP, PNP, signal pure
PNP.
and basic.
The thing is you see at meter, the arrow coming in. You see right here. At the beginning, we already telling you.
Green base.
You see that? Arrow coming in. P and P. Arrow coming out. And PN. Yeah, just a deal for the guy. Just for a while, you can get along. Okay. Now, this is a PNP. Okay. And if they want to do calculation, they already given you everything here. Okay, formula. If you confusing, okay, next meeting, I will go over for you. Okay. PNP biasing with a negative power supply. If now you get a negative power supply, okay, how do we calculate it? This formula already given to you here.
PE,
Okay. Yeah. Like if you want to calculate the VBB,
BCC times
VBB equal minus VCC times R2 divide R1 plus R2. Voltage divider. Same thing like P and PF. VE,
resistor.
you know that is the base. That is the collector. That is the admitter. And this will be a PNP. The arrow coming in. Okay? So if you want to calculate the VE, VE means from here to the round. They said VE equal VBB. That
Yeah.
VBB right here. Plus 0.7. You understand it? This diode on. Positive here. Negative here. 0.7. Okay. And also the formula calculate IE, IB, IC, VRC, VC. Okay. You try it. And next meeting, I go over for you. This is the last one. Darlington connection. That means you can get Q1.
The Lincoln. Connect to
Okay.
Lincoln transistor.
And Q2. Now, they connect output of Q1 to input of Q2. Okay. What they want? They want the beta 1,
NP.
beta 2. That means they
NP.
try to get the big current gain.
Mhm.
If you get 100, you get very big beta. Okay, that's only thing they want. So whenever you working with this circuitry, you have to be very careful. If you touch a round into the output here, they cook right away, burning it. The thing is the current is too high. Okay, you can make that easy. Get first transistor connected where you can get a Darlington connection. Or you can buy one IC. They already built inside. Okay. Darlington transistor are manufactured with a transistor in 1K. That means they put everything into 1K. Okay.
Hey, Mr. Pham, real quick, what did you say caused the cooking? What caused it to burn?
The thing is when you get a disconnect to the route. Okay. You see what I'm saying?
No, say that again.
Disconnect to the route.
What connects to the ground?
Output here. You know why? When you're working, you're using the meter. The route of your meter touch into here. That means they connect to the route.
Is that good or bad?
They burn right away.
So you're saying you don't connect the meter to the ground?
Now you connect your meter to the route of the circuitry. However, for some reason that connect into this area, then you get a big problem. Or when you're using an oscilloscope, the route of the oscilloscope, if they touch into this point, okay? If they touch into this point, they burn it right away. So when you're working with a Darlington circuitry, you have to be very careful. You're using oscilloscope, you can get a route of the scope. Or meter, you get a route of the meter. And normally that connect to the route. For some reason, this output touch into that route, then burn right away. The thing is sometimes, the whole lecture for one day, it's not really you can follow it exactly. Okay? We have to be revealed to you. Okay? A certain thing you have to know. Not everything. Okay? But the very basic. Okay? You have to understand. Now, DC bias, that means we're using the power supply DC to make the transistor working. Okay? And the transistor can be using like the switching. You turn it all open or you close it. That means cut off saturation. Or you can using transistor to make the amplifier. That means they amplify your voice. Okay. Then they will be in amplifier. Okay. So any question, anything? No? Okay, if it's not, okay, so hope all of you guys get a good weekend, okay? And we'll see you on Monday. Okay.
Thank you,
Good night.
Professor
Thank
Sam.
you.
Thank you.
Mm-hmm. Bye
Thank
bye.
you.
Bye.